Hello everyone. So welcome to the third lecture of the physics optional. Yesterday we ended our discussion on the three conservation laws, and then we were beginning to talk about the conservative and non-conservative forces. Okay. Then we discussed the few of the properties of the conservative forces. That is, first, any conservative force can be written as the gradient of a scalar function. That is, f is minus gradient of a scalar function phi. Okay. And the second thing we discussed and we also derived mathematically is that if a conservative force is acting on a system of particles, the work done by the conservative forces is independent of the path. So if conservative force is acting on a particle in this direction and the particle goes from point 1 to point 2, the work done by the particle, that is integral of dw, is equals to minus f dot dr, and this work done is independent of the path taken. Okay, which means that if the same force is acting on the particle, then the particle chooses this path, the work done will also be the same. Similarly for any other path. Okay, and then we derived this mathematically also. Then after that, we started our discussion on the central forces. So central forces, as we discussed in the last lecture, are the forces which depend radially on the distance. Okay, so if there is any force, F, such that this force is a function of f of r. Okay, so if this is the source of the force is a function of r, which means that the force will change radially outwards. Okay, if you go outwards from this point in any direction, the force, the properties, the value of the force will keep changing. Okay. Now, what this radial force means is that if the radius is remaining constant, okay. So if there is a particle, so this is the source of the force. Say there's imagine a gravitational force such that the sun or the moon is here, and say a point particle is here. If this particle moves along the path such that the radius is constant, there will be no change in force, because the force is not dependent on any other angle, theta angle or the phi angle. It just depends upon the radius. So if the particle goes from here to here, no change in force. But if it here moves slightly outwards, there again will be a change in force. Okay. So central forces depend upon the radial direction. So no dependence on theta and phi directions, or for that any other directions. Okay, so this is the basic concept of the central forces. Now we have that so we have started with central forces. Now the thing is, this central force which we talked about, as we discussed in the last lecture also, is a conservative force. So the larger umbrella term is the conservative forces, and within that umbrella term comes various kinds of forces. So there are various kinds of conservative forces. So one of the type of conservative forces is central forces. Okay, and there are many other forces also which are also conservative in nature. And the forces which are non-conservative in nature, as we discussed in last lecture, are usually the kind of forces which try to resist the motion of the particle. Okay, so this is a conservative force. And non-conservative forces are generally like, so we have non-conservative forces, they generally try to resist the motion of the particles. So it's such as the frictional force we have. frictional force. We also have the viscous force in water. So what exactly the frictional force does? So if a body is moving on a surface, okay, so there's a body which is moving on this frictional surface, and if you're applying a force on this body to set it in motion, there's a frictional force which is acting in the opposite direction. So this frictional force tries to resist the motion of this body which is going in this direction, okay, and in this way there is some energy loss. So if you are giving some energy to this body to make it go forward in using the force which we are applying, this frictional force will act in the opposite direction, and as a result there will be a dissipation of energy, okay, and that is why, since the energy is not remaining conserved, okay, the total energy of this total system, the person who is applying the force on this particle, the total energy is not remaining conserved because it is getting dissipated due to the frictional force. The net energy of the system will not be conserved, and as a result it's a non-conservative system, and this force is a non-conservative force, okay. Similarly, we have the viscous force in water. So if this is some cross section of the water in an ocean, and if the ball is going, say, in this direction, we throw a ball inside the water which is going in this direction, the water will provide a backward force on the ball because there are water molecules all around, and as the ball moves through these water molecules, it strikes those water molecules, and as a result there is a friction. There's a kind of friction with the ball of the water molecules, and as a result there's again a net loss of energy of the ball, and this is the reason the ball stops after some point, okay, because there is a net dissipation of energy due to the water molecules which are acting against the ball. So all these forces which resist the motion of any body, be it due to the surface, be it because the body is in water, or in many other cases also, are called non-conservative forces. So we'll go more into the concept of central forces, but we'll use the basic notion of the central forces for now to proceed ahead with the next topic, which is the center of mass, okay. So we will just go. Now, what is the center of mass? Okay, so as we said before, in each of these topics, I'll be going very basic. Okay, there must be many students who already know the concept, and they may feel like it's getting slightly repetitive. But there are many other students who have some basic issues regarding these concepts. So in all of these concepts, we'll be starting from very basic, from the scratch, so that everyone in the class knows what we are dealing with. So when we say the center of mass, what we mean is that just imagine there is a body, okay, and it has a uniform mass distribution, okay. So all the particles inside the body are uniformly distributed. And if there is a force acting, we are applying a force, external force, on this body, okay. Now, usually when we talk about in many numericals using the Newton laws, till now what we have discussed is the force is acting on a particle, okay. The forces are acting on this particle, this point particle, and as a result, the point particles get set in motion. But what if this force is acting not on a point particle, but on a big ball or some object which has a uniform mass distribution? To simplify the physics, because if we keep taking this bigger body, the physics becomes slightly tedious, because you're applying the force here. Now you don't know how this whole body will behave because it's no longer a point particle. So what we do is, to simplify the calculation, we assume we represent this whole body by a single point somewhere inside the body. And we say that this external force which is acting is not acting on this whole body, but on a single point inside the body, okay? And this point is chosen in such a way that if we apply all of physics on this point of whatever the external force is acting, we get the same equations of motions as in we'll get if we solve the larger system of this ball. So you can actually, it's a very complicated system, but you can actually, what you can do is say that where, at which point exactly the force is acting in which direction. And then you can measure, say, the distance from the center, and this is making angle theta, and then work out all the, all the equations of how this whole body would react, which will be a tedious calculation. So what we do is we just represent this whole body by a single point, and we say that the force is not acting on the whole body. Instead, if this is the body, instead of just a point inside the body, and we say the external force is acting on that point. In this way, the whole calculation becomes very easier. And so, but this choice of this point inside the body is not an arbitrary choice, because if we choose any other point inside the body, our result, which is basically we want to do is we want to find how this ball will behave as a function of time, what will be the motion of this ball, in which direction it will go. All these things, if we choose an arbitrary point, they won't turn out to be the same. Okay, so we need to choose a unique point inside the body, which has a certain property, such that if you apply the whole force on just that point, we can get the same equations of motions which we'll get if we solve for the larger system. And this point is called the center of mass. Okay. So if it's a uniform body, so if this body has a uniform mass distribution inside, as in if you take any small piece, any cross section of this body, there is some density of the particles inside. Okay. And this density is same all over the body. If you take any cross section, no matter what shape, the density is always same. So as a result, the whole body has a uniform mass density. So in that case, the center of mass will always lie at the center of the body. Okay. But if this body has a non-uniform mass density, in the sense that if you take this cross section, it has a higher density of mass. This cross section has a lower density of mass. If the mass is distributed arbitrarily in various densities all over the body, then the center of mass won't lie at the center. It will lie at some other point. And that we need to work out. That we need to work out mathematically. Okay. So from now on, whenever we encounter any extended bodies and not point particles, what we'll do is when we want to solve how the body will behave as a function of time, that is its equation of motion, what we'll do first is calculate the center of mass of the body. And after that, we'll apply all the laws that we have, all the force laws on that point particle, and find the equation of motion of that point particle. And then we'll say, okay, this is also the equation of motion of the larger body. Okay. So this is it. Now what we'll do is we'll calculate the center of mass. So now we need to calculate how to find the center of mass of any kind of body. So initially we'll start with a very simple system, that is center of mass of two particles. Okay. Later on, we can use the same result that we get to find the center of mass of n number of particles. If there's a very large body and it has, say, 10,000, 20,000 particles, we can use the same general result to find the center of mass of a larger body. So we'll find the center of mass of two particles. So this is our coordinate system. Assume first particle is located at a distance r1 from the origin, this first particle, and the second particle is located at a distance r2. Okay. And there's an external force which is acting on these two particles. So, and it's a central force, so it's acting radially outwards. So from and it's acting from here. So this is the source of the force, and it is acting radially outwards on any particle which is there. If the particle is here, this force will be acting like this in this direction. Okay. But now we are just taking two particles. So on particle 1, the force which is acting is F1 in this direction, and the particle 2, the force is acting F2 on this direction. Now these two forces, since it's a central force, these two forces, the magnitude of these two forces would have been the same if they would have been at the same radial distance from the center. Now, since we are taking a general system, so they may be at a different distance from the center. So that's why taking F1 and F2 and not the same F. So there is a force F1 on particle 1 F2 on particle 2. And these two particles are also interacting because of their each other forces. So particle 1 is also exerting some kind of force on particle 2, and particle 2 is also exerting some kind of force on particle 1. So this is the line joining the two particles. So particle 2 is exerting a force F12 on particle 1, and particle 1 is exerting a force F21 on particle 2. So F12, what it means? F12 is nothing but force on first particle due to the second. Okay, and F21 is nothing but force on second particle due to first. So particle 2 is exerting a force F12 on the first particle, and the particle 1 is exerting a force F21 on the second particle. Now this force could be a gravitational force. We can imagine that this is the sun and these are any two of the planets, just for our consideration purposes. So sun is exerting a net force F1 and F2 on both of these particles, on both of these planets, and these planets are also exerting gravitational force on each other. So if this is Earth, it has some gravity of its own, and if there's a planet nearby, it will exert a gravitational force on that planet too. Okay, so this is how these two particles are interacting with each other also, and there is a net external force which is acting on both of them. Okay, so if this is the case, what we have is, for our equation of motion, that F of 1, or we say the total force acting on particle 1 is F1 plus F1 of 2. Okay, F1 is external force and F12 is the force on particle 1 by particle 2. And this is nothing but M1 mass of the particle 1 times the acceleration of the particle. Okay, so total force is nothing but mass times the acceleration. So mass is mass of particle 1, acceleration is acceleration of particle 1. So we have chosen R1 here because R1 is the distance from the center of that particle 1. So we keep the same notation. So it's okay. Similarly, on particle 2, the net force is acting is F2 plus F of 2, 1, which is M2 d square R2 upon dt square. All right. So we have these two equations. Now what we do is, just remember the larger objective, we need to calculate the center of mass for these particles. We need to find an expression for the center of mass. And once we find the expression, then we'll calculate what exactly is the center of mass. So we have these two equations. Now what we do is we add these two equations. So then we'll have, so this is equation 1, this is equation 2. We add these equations. So we have F1 plus F12 plus F2 plus F21 equals M1 okay. So we have added these two equations, this and this and this and this, and then we equate. Now if you see, F12 and F21 are nothing but reactive forces, in the sense that F12 is the force exerted on particle 1 by particle 2, and F21 is a force exerted by particle 2 by particle 1. So they are action reaction forces. So using Newton's third law, which we have already discussed, we know that if there is a force acting on a particle, it exerts a similar force on the first particle. Okay. So using Newton's third law, of motion, we have F12 equals F21. Okay. Because these are action reaction forces. So which implies, or F12 is negative of F21. Okay. The magnitude of this will be same, F12 if F21. But of course, these two forces are acting in opposite direction. F12 is acting, F12 is which is the force on 1 by 2 is acting in this direction, and F21 is the force on 2 by 1 is acting in this direction. So when we write this equation in vector form, there will be a negative sign. Of course, but the magnitude, of course, will be the same. So we substitute this 3 back in this. So what we get is these two terms will cancel, and we have F1 plus F2 equals all right. Now F1 and F2 is nothing but the total external force which is acting on the combined system. So system in our case is particle 1 and particle 2. And so the total force which is acting on both of these particles, total external force, not the forces which is acting within the two particles. The total external force is F1 plus F2. So this is nothing but F external equals, now since mass is remaining constant, this m1 and m2 are constant, we can take the double derivative outside. So this will be g square by dt square m1 r1 plus m2 r2. Okay. So we have yeah. So now what we do is, as we discuss the concept of the center of mass, that if we have extended body, we assume that the total external force is acting not on the whole body, but on a center of mass of the body. Okay, such that the results of the equation of motion, if we solve for that point of that center of mass, will remain the same. So if we have the extended body, we calculate the center of mass, and we say that if external force was acting on this whole body, we can apply the same external force on this single point, and we'll get the same laws of motion. So now if we have, instead of the extended body, now we're taking just two particles, and there's one F1 force here, and this is F2 force here. Now what we assume is there is, and this is the coordinate system, R1, R2. Now what we assume is there is somewhere in between them a center of mass, some point, we don't know what the location is, and we can assume that instead of solving for this big system of two particles, we can assume that this net external force, which is F1 plus F2, is acting on this point. Okay, this is an arbitrary point. There is nothing physical over here. It's just we choose a point like this so that we can apply this whole force on this point and find the equation of motion of this point particle, and then we can back substitute to calculate how these two particles will behave. Okay, so what we do is we assume this point is at a distance r, center of mass. Okay, because this arbitrary point is nothing but the center of mass of these two systems, of these two particles. So then we can write this as F external equals n which is equivalent to. So instead of writing f external as this, in this expression we have assumed that there is a combined mass of m1 plus m2. There is a single mass, and this force is acting on this combined mass, and the radial distance of this combined mass is r vector is our center of mass. So instead of solving for these two, we are now in this we are just solving for this point. Okay. So again, I'm repeating. Instead of solving, we're saying that f external is acting on these two particles, m1 and m2. We have, using our concept of center of mass, here we have assumed that this force is acting just on this point, which has a mass m, capital M, and this m is nothing but the mass of these two bodies combined, and it is at a distance r center of mass from the center. Okay. So now if we compare these two equations, because these are the same, we get, again taking the double derivative outside. Hold on. Yeah, so in this equation, there's a double derivative outside here also. So we need to put this here. Okay. So now if we compare these two forces, two equations, we take the double derivative here outside. So we'll have equals okay. Now comparing these two terms, we get that m r center of mass equals m1 r1 plus m2 r2. So it implies okay. This implies that this position of center of mass, r center of mass. So r was nothing but the radial position of the center of mass with respect to the origin. Okay. So our center of mass is m1 r1 plus m2 r2 upon capital M. Okay. Where capital M is nothing but m1 plus m2. So here we have found the expression of center of mass for two particles. So now what we find is that instead of two particles, if there are three particles or four particles at very different distances from the center. For example, if this is our coordinate system, and there's particle 1 over here, particle 2 over here, 3 over here, 4 over here, and these are distance r1, r2, r3, and r4. Okay, these four distance. And if you want to calculate the center of mass of this system, it turns out it is nothing but what we do is our center of mass is, so here we have mass of first particle times the radial distance of the first particle plus mass of second particle times the radial distance of the second particle. And if we have four particles, we just need to add their masses times their radial distance to this same equation. And the capital M here was m1 plus m2 because we had just two particles. But the capital M in this case will be m1 plus m2 plus m3 plus m4. So the formula of this will become now m1 r1 plus m2 r2 plus m3 r3 plus m4 r4 complete divided by capital M. Okay, and this capital M is nothing but m3 plus m4. All right. Similarly, if we have n number of particles, if there are n particles, the general expression for the center of mass becomes summation I, or let's start with the easier way. It will be R1 plus M2 R2 till Mn Rn divided by M1 plus M plus Mn. Okay, and this is nothing but summation of I goes from 1 to n Mi Ri summation I goes to 1 to n Mi. Okay, so if there are n particles, we need here sum over the masses of all the particles, and this summation, and this is nothing but the same expression but in a condensed form. Okay, so this expression gives the center of mass, the radial coordinates of the center of mass, if we have n particles in the system. All right, so just see this once if there is any issue. All right, so now here what we consider is these n particles were at a separate distance. They were separated by some distances, and they were scattered at different points on the in the coordinate space. But what if we have a continuous system of particles? For example, say a rigid body. If you have a rigid body, all these particles are totally packed with each other. Okay, in that case, although the general expression kind of remains same, but then what we have to do is, instead of summation, here we did summation because there were finite number of particles. Since in a rigid body, it's practically infinite number of particles, but instead of summation, we do integration. So that will be integral of R dn upon integral of dn. Okay, you can see this expression is very similar to this expression. Here it was summation of mass of first particle times the coordinate of that particle divided by the total mass. Here also the mass of one particle, that is dm, because if there is an extended body, we take a very small area, practically very small area, and that will have dm mass. So what we do is integral of, and r is the coordinates of that. So this is r, and this is dm. And what we do is we integrate over the whole body. Okay, so there will be dm, 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 dm. This is also dm, some dm, 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 dm. So we integrate this over the whole body to get the total expression of this. And similarly, integral of dm is nothing but integral of dm, 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 dm all over the whole body, which will give us the total mass. Okay, so this is the expression for our center of mass if it's a rigid body. If the particles are arranged, are tightly packed in a continuous fashion, it's a continuous system of particles inside a rigid body. Okay. So this is for finite number of particles, and this is for practically infinite number of particles.